Okay, thank you and welcome to an overview discussion on CXL or Compute Express Link. So my name is Glenn Ward. I'm a Senior Director in Technology Development in Microsoft Azure. I'm also a co-chair of one of CXL's work groups. And in my talk today, I'll provide an introduction and overview to CXL. I'll talk about the CXL standards body or consortium itself. I'll cover CXL use cases as well as the core technology, and I'll end with a number of links that will provide you more information for where you can go to join, how you can consume the CXL specs, and what CXL can mean for your company. So to start, there are a number of use cases that really informed our design choices that we made for CXL. And these constitute effectively the overarching trends that we see in computing. So at current course and speed, and I think this is true certainly in Azure, but true of other tier one hyperscalers in general, we project out that for cloud computing in particular, the proliferation of cloud computing really will in the future put a strain on cloud computing architectures, or sort of the classic server and rack architecture that constitutes the cloud. The cloud delivers amazing capabilities, the ability to scale, the ability to burst workloads on demand. But I think as workloads become increasingly complex, we're seeing that something other than just increasing the feeds and speeds of the underlying infrastructure becomes extremely important. I think it's probably doubly true for artificial intelligence, machine learning, and data analytics. Also at Microsoft, we're seeing machine learning models with just a huge number of parameters, in some cases more than 1 billion parameters for the most compelling ML scenarios like drug discovery, real-time machine vision, and so on. And in those cases, I think it's true in general that a model's performance begins to decrease as it's really extended out across increasingly large numbers of nodes. And we run into some real impediments for I/O performance and trying to leverage today's interconnects to move all of that data and keep all of that memory updated. I think lastly, the movement from the cloud to the network edge presents some challenges as we forecasted out as well. So network operators for the last few years, traditionally have run specialty comms purpose-built hardware, but the capabilities of cloud hardware have been compelling, giving them performance and fungibility. But once you layer in the demands for speed and performance that applications that hang off of 5G need, you end up with a real strain on the network edge. Let's dig into this a little bit more deeply. Specifically, why the need for an entirely new class of interconnect? And I'll describe this by going into the diagram on the upper right. So the gray box represents the architecture within a node, or the constituent components with a node. And there are a few things to call out. The blue box at the top is standard memory. So think of DIMMs just attached to the host, hanging off of the CPU. The green box below represents memory that's part of accelerators. So things like high bandwidth memory that could be part of a GPU or an AI accelerator. Then across the middle of the gray box in the upper right, we see the constituent components of a server. So we see host processors or CPUs with a number of cores. We see the GPU, we see a programmable FPGA, we see something like an artificial intelligence purpose-built accelerator. And then we see different varieties of NICs, like a standard NIC or an intelligent NIC. Now, the paths to memory that are described in white function and work well today. The paths, though, to memory that are described in red really don't function, not with a level of solid interoperability across implementations, and typically not without exotic hardware to enable those red paths. So let's pick some examples. You're really not going to get those accelerators talking to memory to the host over PCI DMA for the most part, not without exotic solutions. And those exotic solutions kind of come at a cost. The The same thing for PCI Express peer-to-peer, the same thing for CPUs trying to access uncached memory on accelerators. And these are the problems with today's environment. The future that CXL takes us towards is represented in the bottom right. So all of those memory paths described in green are now open to us. We can get CPUs accessing memory, like high bandwidth memory on accelerators, in a write-back fashion. We can enable accelerators in the middle talking to memory hanging off of a host with standard memory semantics, load store semantics, in a coherent way. We can access DMA across PCIe. So this is really exciting to us, and it's this CXL-enabled world that we're moving towards. Let's get into Compute Express Link in a little bit more detail. So if we look at my diagram on the right, what's the sweet spot for CXL? Where does CXL, what's its primary focus area? We really look at CXL as providing the processor interconnect of choice in between processors and in between devices and hosts with computational capabilities at the node level. So really, node level computing is our sweet spot. That means that it really lives below the network or fabric or topology of connectivity choices stitched together TORs across multiple racks, and it lives above interconnects that tie together the components of the SoC, or tie together the components of a processor within a given package. Now, the capabilities of CXL that let it function so well at node level are that we certainly deliver a high bandwidth communications, and we've absolutely made as a primary design point the ability to do that at incredibly low latencies. We stand on the shoulders of PCI Express to do that. I'll be describing that in my upcoming slide. And then, as mentioned earlier, our targets are the high-performance computational workloads like AI, ML, high-performance computing, and network gear or comms gear. Let's get into CXL in a little bit more detail. So a helpful way to think about what makes up CXL is that it leverages or really stands on the shoulders of PCIe below it. And this translates to a lot of rich capabilities that we can leverage and build on. The first that we get, thanks to PCI Express's compatibility. So CXL devices use the same connector and electricals as PCI Express. If you look at the BY16 connector shown there in blue, that connector can receive either a plain vanilla BY16 PCI Express card, or the same connector can receive a BY16 CXL card with no changes, with no mods. Same electricals, same mechanicals. Closely following compatibility is a flexibility and fungibility that leveraging PCI Express gives us. And by that I mean, accelerator companies don't have to make difficult binding choices of which to support. They can support both. So there's no need to fracture or fragment their SKU lineup. The same accelerator can operate in PCI Express mode in systems that aren't CXL enlightened, but in those systems that are CXL aware, their accelerator or device can easily switch to CXL awareness and deliver CXL-based capabilities such as memory coherency. Now, these capabilities are enabled because we take advantage of PCI Express version 5's ability to advertise alternate protocols. That capability was introduced in PCI Express version 5 for the first time, so it hadn't existed previously in previous generations of PCIe. What that means is in the design of a system, systems designers don't need to build separate ports, and they get tremendous efficiencies from leveraging the same infrastructure. Now, the speeds that we operate at are pretty amazing. Using PCIe Gen 5 for our foundation, CXL devices will function at a full 32 gigatransfers per second per lane. Across 16 lanes, it gives us I/O of 512 gigabits per second in each direction. Adding 512 gigabits together times 2, we get a terabit per second of total aggregate bandwidth. And that's something that we take advantage of to use to maintain memory coherency between the CPU memory space as well as the memory on devices. This allows for more efficient resource sharing and you can move your workload seamlessly between the different computing entities in your node. Now let's talk about the CXL protocols in more detail. My green box on the right describes the totality of the CXL protocols. There are only 3. And that's a specific design choice to make implementation easy on the device vendor who's choosing to implement CXL. So the first is CXL.io. This is a lot like PCIe.io. And this obviously performs the I/O function of the stack. Things like device discovery, handling interrupts, handling device personalization, and most importantly, capabilities like bulk DMA are delivered here. CXL.io is mandatory. Every CXL device must implement it. Now, our other 2 protocols are optional depending on what type of device class the implementer chooses. So CXL.cache allows the device to cache system memory coherently and with low latency. This means the device can cache the host memory. Now, CXL.memory is the same thing, but in reverse. CXL.memory allows a processor to access device-attached memory. So let's talk about which one of these might be used in this diagram. So if a host processor, the gray box in the middle, wants to access the blue box, which is memory hanging off of the device, something like high bandwidth memory, then CXL.memory is the protocol that enables that capability for the processor to access device-attached memory. If a device, the gray box on the right, wants to access system memory, it implements and uses CXL.cache, so it can go straight to processor memory. All of these capabilities are multiplexed at the logical PHY layer, which we see goes directly to the physical PHY for PCIe or PCI Express. Now, let's go through a little bit of features and benefits. All 3, and I'll talk more about use cases in a moment, all 3 elements have as their design point minimizing the latency by having an incredibly efficient stack. So I'd say foremost in CXL's development was making sure that we optimized for the lowest latency possible. We have spectacular bandwidth below us that we can leverage thanks to PCIe Gen 5, but the opportunity really lay in squeezing all the latency out of our stack. So if you take a look at the diagrams of the 2 stacks, the CXL stack and an alternate stack, you'll find that mechanically, structurally, they're very similar. And that's by design. We didn't want to introduce any unnecessary shims or layers that would add latency. And that as a result, we can access directly, go straight from the transaction layer to the link layer, straight from there to the multiplexer, straight from there to the PHY. And the same thing happens in reverse for signaling coming over the bus. We can go incredibly quickly up to the transaction layer. Exactly what the device needs to perform at fast rates. Now, the second on our list of critical design points was making sure that we made CXL as easy to implement as possible for vendors so they could design accelerators or things like memory controllers with a really low burden or a low hurdle to clear to implement CXL. And I show this by taking a look at something like a cache coherent interface model with a symmetric CCI protocol on the left. All of those orange arrows in my accelerator device on the far left, those represent work, right? Like that is challenging work to implement, to be able to stitch together your accelerator engine to your caching agent, stitch it together with your home agent, ensuring that that can talk to your memory agent and that all of that can talk cache coherently to the CPU. By contrast, if we take a look at the asymmetric protocol that CXL implements, that really means that the burden's on the host. So the complexity is implemented at the host level, and the host does the heavy lifting. And as a result, implementing CXL just really translates to doing some not difficult, practically lightweight shims, so CXL.io and either or both of CXL.memory and CXL.cache in the accelerator. And that gives us a number of advantages. The first is we can enable memory buffering without a coherency burden on the device. Secondly, the device developers can implement CXL without having to worry about the choice of CPU that they choose to interoperate with. CXL provides an amazing interoperability promise thanks to it being supported by every CPU vendor. I'll talk about that in a little bit more detail later on in the deck. And lastly, avoiding the protocol interoperability hurdles and roadblocks that just come from a challenging implementation. That's really sort of the bugaboo of protocol implementation, is that complexity translates to long bug burn downs and significant interoperability challenges that we don't have with CXL. Let's talk about those use cases in more detail. So there's a wide span of supported use cases that are really exciting. These span processors, memory, accelerators, GPUs, GPGPUs, FPGAs, and on down the list. So the three boxes depict type 1, type 2, and type 3 use cases. That's CXL parlance, and I'll explain what those mean. Type 1 means, a prototypical example is something like a NIC wanting to access in a way memory that's attached to the host processor. That NIC or intelligent NIC has to implement CXL.io, and it would also implement CXL.cache so that it can coherently access host processor memory. That's type 1. Those are caching devices or accelerators on the left. The middle box, accelerators with memory, these implement CXL.io plus, most importantly, CXL.memory and typically CXL.cache as well. These devices with their own memory enable the processor to access sort of a rich field of HBM hanging off of accelerators. Now, lastly, are device categories that don't have any computational element at all. These are memory buffers. This enables fundamentally memory expansion. So the host processor in the rightmost box can access much larger swaths of memory that are made available to the host processor. And these swaths of memory can, of course, be DRAM, but it's pretty exciting to see the new classes that are adopting CXL, such as storage class memory. Now let's revisit the heterogeneous computing slide that I began with at the beginning. Heterogeneous computing fundamentally is enabled with CXL, where compute can happen on specialty compute engines in the variety of heterogeneous processors that are within modern day nodes. So CXL provides a number of benefits thanks to enabling heterogeneous computing, such as we enable both user mode and kernel mode access to memory and the ability to transport data and maintain coherency in the transport. The access that we provide in CXL occurs at really low latency in both directions, both host to device and device to host. For things like machine learning models, CXL makes it super easy to populate and update operands. It's frankly trivial to push out a new operand like a sigmoid function or a hypertangent, and all accelerators perform the computation. All the data is updated and kept coherent and consistent. And lastly, the ability to borrow memory and have a more balanced, fungible system with bottlenecks removed is a key attribute of CXL. So in summary, CXL provides a coherent interface leveraging PCI Express. Its number one design point is providing low latency. It simplifies the burden of development for implementing cache coherency in accelerators or in devices. And as an open standard, we've got spectacular industry support, and we've been growing at a tremendous pace, which leads me to our next section, which is to talk about the consortium itself. So as of the time of this presentation, we're actually at 99 members. By the time you view this, I think we'll be at 100, given that we've been growing by a number of members practically every week or every 2 weeks are joining our ranks. There's a few noteworthy items. I mentioned this in a previous slide, but in all my years of being in the industry, I haven't observed this before, but CXL has as its members all CPU manufacturers. So that's kind of a first, practically a hat trick. It presents a wonderful story for device companies implementing CXL, is that you don't have to make a hard choice. You don't have to choose one CPU architecture or another, or maybe place a bet that a future architecture may come on board. CXL today has as its members all the CPU architectures represented across a multitude of companies. So implementing CXL means that you have open to you x86, x64, ARM64, and the Power series of processors using IBM's architecture. So that's frankly pretty fantastic, and opens up the entirety of all sockets enabled by all CPU architectures to people that are making CXL devices or making memory expanders. Now, there are two levels of membership available for participation in CXL. The first and lowest class, or the lowest on the tiering, is the adopter level membership. A few things about adopters. Adopter membership is free and gives your company access to the final releases of CXL specs, and B, gives your company IP protection that we outline in our IP policy and membership agreement. The next level up, the contributor membership, provides a lot of compelling benefits. The majority of our members are contributors. Contributor membership provides a number of benefits. The first is being able to participate in the CXL workgroups and influence the direction that the technology goes. The second is access to the intermediate specs. So you're able to see the dot level intermediate specs long before they become finalized, so you can make design choices and get a leg up on your own implementation. Currently, membership costs, get asked that question a lot, are at the, as I mentioned, at the adopter membership level, it's free. At the contributor level, it's $20,000 for the first year and $10,000 per subsequent year. I'm also excited because exactly a month ago, we announced a formal industry relationship between ourselves in CXL and the Gen Z Consortium. We signed a memo of understanding, and this creates a great framework to collaborate and do some specific design work. So specifically, we're going to have a number of common work groups between CXL and Gen Z that defines how we bridge the two protocols. That's really exciting to me because in the same way of the spirit of open standards, the spirit of low barriers to entry, to become an adopter, to move up to contributor, low barriers to implementation, this removes a barrier for a device implementer to have to make a choice of should my device be a CXL device or be a Gen Z device. We saw in CXL some fantastic momentum that Gen Z was having in the fabric or network space, much focused on the rack level and sort of inter-rack level. And that's just a wonderful complement to our focus today, which is really node level computing. So we're really excited about our relationship with Gen Z and what it means for companies implementing CXL. Now I'll wrap up actually, and I'm going to give my audience a call to action. The first is to join the CXL Consortium. It's a fantastic consortium with a ton of activity. If you want to, in my humble opinion, come to a standard that's really hot and moving incredibly quickly, CXL is the place to come. Encourage you to follow us on social media because we are moving at a very rapid clip. So you can follow at Compute Express Link on Twitter and also follow us on LinkedIn. And today's material is really just a starting point, but we've got a wealth of material on the Compute Express Link website, as well as tutorial videos and a host of other videos up on YouTube. So I encourage you to check out the CXL Consortium channel on YouTube. That concludes my presentation today. Thank you very much for attending, and I look forward to seeing you at CXL.